All right, PVT behavior of gas mixtures. You're familiar with this, how to do this calculation for pure substances like any ideal gas. What if we have a mixture of gases? So we are familiar with this equation, PV equals ZRT. We're familiar with this. Z called the compressibility factor, which is a measure of how close the behavior of the gas is to the ideal gas behavior. So we can actually use this equation for a mixture of gases as well. It's not limited to the pure gas. So let's talk about that. There are two basic laws that help us. One is Dalton's law of additive pressures. So the assumption of Dalton's law is if you have a mixture of gases, in this case, if you look at the figure, you have gas A and gas B, and they're mixed together. So the assumption is that the temperature of the mixture is the same as temperature of each of the gases or the components in the gas, which is a good assumption. And the other assumption is that each gas is treated as though it is occupying the entire volume. So for gas A and gas B, volume V is the same as volume of the mixture, and temperature T is the same as temperature of the mixture. But the pressure of the mixture is the sum of pressures of each of the components, PA plus PB. These component pressures are called partial pressures. So Dalton's law tells us that the gases are treated, the components in the mixture are treated as though they are occupying the entire volume, and they are at the same temperature of the mixture, but each one has a partial pressure. When you add those partial pressures together, then you will have the pressure of the mixture. Another law is Amagat's law, which is a little bit different. So the assumption in Amagat's law is that when you have a mixture of, let's say, in this case, two gas components, the temperature of each gas is the same as the mixture temperature, similar to the previous law. But in this case, the gases are treated as though they have the same pressure of the mixture. So the pressure of gas A is the same as the pressure of gas B, and both are the same as pressure of the mixture. But each gas is assumed to occupy a partial volume. When you add those partial volumes, you get the total volume of the mixture. So we have VA plus VB, which will be equal to the volume of the mixture. For ideal gases, mixture of ideal gases, meaning all components in the mixture behave like ideal gas. Doesn't matter which law you use, Dalton's law or Amagat's law, same result. You will get the same results, the exact same results. But if the mixture is consisted of real gases, non-ideal gases, then the results are not identical. If you select one law or the other, you get a little bit different results, and the results are, of course, approximate. So just in mathematical form, pressure of mixture according to Dalton's law is the sum of the partial pressure of each component at the mixture temperature and mixture volume. Amagat's law tells us that volume of the mixture is the sum of partial volume of the component at the mixture temperature and pressure. So according to Avogadro's law, if you have a mixture of oxygen and nitrogen at 100 kilopascals and 400 Kelvin, having a volume of 1 cubic meter. So for example, it could be pressure is the same, temperature is the same for each component. So for example, 0.3 cubic meter is occupied by oxygen and 0.7 cubic meter occupied by nitrogen. When you add them together, you get the mixture volume 1.